Okay, let's get started. The last speaker for today's session is Professor Jin Long from Tsinghua University. He will be presenting on semi-classical measures on compact hyperbolic surface. Uh, and Professor Jin Long is awarded the Frontiers of Science Award. His work lies at the intersection of PDEs and dynamical systems, and he has made significant contributions to the understanding of quantum chaos and semi-classical analysis. So let's welcome Professor Jin.
Yeah, thank you. Thank you for the introduction, and it's an honor to receive this award. And I'll thank the committee member on behalf of my co-author to receive this honorable award. And I'll be talking about mainly about our result. My result with Semyon Dyatlov from MIT on semi-classical measures on compact hyperbolic surfaces. But I should also mention that our result has been generalized further to arbitrary surfaces with negative curvature with in a later paper with also with Dyatlov and Lindenstrauss measures. So okay, okay. But we'll focus on the on the question on hyperbolic surfaces, which is just a compact surface with constant Gaussian curvature -1, and we'll study the Laplacian eigenfunctions on such surfaces. And the key feature of our result is in the field of so-called quantum chaos, because the so-called geodesic flow on such surfaces are a very classical model of classical chaos, and the study of Laplacian eigenfunctions with some sort of quantization of geodesic flow. So it's kind of the quantization of the classical chaotic system. And the key ingredient in our study is well, it's not maybe not a very new tool, but it's been almost 10 years. So it's a tool called fractal uncertainty principle, which is a harmonic analysis statement. Okay, so let me state a very simple version of our result, so which can be easily understood. So, so for any compact hyperbolic surface, and you pick any empty open set on the surface, our result shows that you can always find a positive constant, which only depends on the surface and the open set, such that any normalized Laplacian eigenfunction has a uniform lower bound, the C here. And the important thing to see here is that this constant C does not depend on the eigenvalue lambda, which I know lambda squared. So lambda will be the frequency. So in general, if you have a fixed lambda, then by unique continuation of the this is kind of a elliptic PDE. So you can use the tools from unique continuation, or either the so-called doubling estimate or like Colin estimate. You can get a constant. You can get a constant, but depending on lambda, which depending exponentially small on lambda. And this form is sharp. In particular, if you have a round sphere, and our result cannot be true for the round sphere if your open set does not intersect the equators of here. So in that case, you only have such a lower bound. So you cannot have a uniform lower bound in the eigenvalue. So so our result really shows that on hyperbolic surface, for any open set, you can have this lower bound. This is a uniform lower bound, and okay, and this is also true for torus, for the flat torus, which has been done by many people, but that is basically a question about Fourier series. So, because the Laplacian eigenfunctions on the torus are just sine and cosine. And also all the results I'm going to present today has been generalized to any surfaces, I mean two-dimensional manifold, compact manifold with no boundary, such that its geodesic flow has this anisotropy property, and that includes all surfaces with negative sectional curvature. But my talk will be concentrate on this hyperbolic surface case because it's simpler. So this paper is like 30 pages, and if you want to read the paper we did, so general surface with negative curvature takes like more than 100 pages. So that's much more technical here. So, and I'll try to kind of explain the key ideas and all the kind of ingredients from different areas in our result. Okay. Okay. So first, let me say that because for any fixed lambda, you have a lower bound. So in particular, if you only care about finite number of eigenfunctions, then this is always true. So our result is really about when lambda goes to infinity. And then you can formulate it in a so-called semi-classical way by taking h, which we understand as a Planck constant, which is 1 over lambda, and it will go to 0. And we reformulate this question in terms like this: so minus h squared Laplacian minus 1 applies to u equals 0. And we want to understand the behavior of this u when h goes to 0. And so you can ask such questions. So because if we normalize the L2 norm of u, then u squared dx will be a probability measure, and you take the limit, it will have weak limit. And of course, it may not be unique, but it will always has some weak limits. So this weak limits will be called the quantum limits. And we want to say, okay, so the best possible case is this probability measure will convert to the volume measure, which normalize. So that will be called the equity distribution. And you can also it's also possible that there may be a sequence which converts to a measure which localize on a very small set. So that will be kind of localization of, in terms of quantum calculus, it's called a scar. So it's like you have a scar on your face. So it will be concentration, so or localization. And it turns out that the quantum limit really depends on the dynamics of the geodesic flow. And the reason, well, the heuristic reason why it works for why our result works for hyperbolic surface, but does not work on round sphere is that the geodesic flow on the round sphere is integrable, but on the hyperbolic surface is chaotic, or more specifically anisotropy. Okay. Okay. So we take a weak limit means we basically we test it with any continuous function, and you convert it to this continuous function, integrate along the quantum limit, and we can further write this u square as a times u, taking inner product with u. But our geodesic flow is living on the phase space, so it doesn't. It depends. It depends not only on the position but also the direction. So I'll take the phase space as the cotangent bundle. And so in order to understand how this is connected to the dynamic of geodesic flow, we have to try to lift this weak limit to the phase space T psi. So that means I'll replace this A here by a function which lives on the phase space. But of course, this two function U here lives on the base manifold M. So I have to define a so-called quantization of A, which will be an operator and applies to U. And this will be the so-called semi-classical limit. Okay, so now let me try to explain what is this called quantization here. Okay, so there are many ways to quantize such a thing, but it turns out that it doesn't matter which quantization you take. So, for example, if you are on Rn, on the Euclidean space, the easiest way to quantize is use the so-called standard quantization, which you just basically this any a here. I will also take this. I will also put the parameter this Planck constant h in this quantization. So that will be basically this operator, which is your first take a Fourier transform, and you sort of multiply by this ax psi here, and then taking inverse Fourier transform from psi to x. Of course, you keep this x here. And in this way, if you have a function only depending on x, only on the base manifold x, then this is just a multiplication because you're just taking the Fourier transform and then to the inverse Fourier transform. And if you only depend on psi, then this is so-called a Fourier multiplier, which is just a formula you just take a Fourier transform multiplied by a psi and then take an inverse Fourier transform. And of course, so we study more general things, which will be called the pseudo-differential operators, so, which generalize both cases, which means A is depending on both x and psi. Okay, so let me quickly explain the basic properties of the quantization and give you such sort of a heuristic. So the basic heuristic here is that this this pseudo-differential operator, this A quantization of A, is roughly like multiplying A on the phase space. So if you have two symbols A and B, you first take a quantization, then it's almost like first take product and then take the quantization. And of course, there is a lower order term in H when H goes to 0. So you can think of this as basically as applying like a multiplication of A onto this function, but in phase space. A second key feature which brings the dynamics into this picture is that if you consider a commutator, which means you have two symbols A and B, you take the quantization of A, quantization of B, but you apply like alpha H A, alpha H B minus alpha H B, alpha H A. So this commutator, let me just write it down. This is just you compare the two different ways of the compositions. Because this operator composition is a non-commutative product. So by the first formula, we know is actually the leading order cancels because A times B is the same as B times A. The next term, it will just be of order H, and it is the quantization of the Poisson bracket of A and B. So this corresponding to the Poisson bracket of A and B. And this is exactly well, if you think of in a dynamical way, this is the Hamiltonian vector field of A applies to B. So HA will be the Hamiltonian vector field of A. So that will naturally brings the Hamiltonian dynamics into this picture once we have this commutator. And we also have this the next several nice properties, which the so-called the Guardian inequality shows that if A is non-negative, then your operator is almost non-negative, and the L2 norm of A is basically the supreme norm of L2 norm of alpha H A is almost like the supreme norm of A, and you also have this so-called elliptic estimate, which is a generalization of the elliptic estimate in the PDE. So, which basically says that if you have two symbols and the support of one, the first is in the open set B is not 0, then you can use alpha HBU to control alpha HAU. So basically, if you have a larger cutoff, you can use the larger cutoff to control the smaller cutoff. So something like that. Okay, and then you can, this quantization also behaves well under change of variables. So basically, this change of variable is just naturally the change of variable on the cotangent bundle. So that's why we use cotangent bundle for the phase space instead of the tangent bundle. And this way you can define a quantization on any compact manifold, and you can have this. You can also have this operator give back to your symbol to get this symbol map, and all the previous properties works on compact manifolds. Of course, this quantization is very non-unique. It depends. You can use like a certain partition unity to do it locally and then piece them together. And this, of course, depending on the partition unity you choose and the local coordinate you choose. But in any case, any two different quantization differs by a lower order term O of h. So when you go back to here, it gives you a lower order term. You take the limit, it disappears. So it doesn't matter which one you take. Okay. Okay, so what we care is on this remaining manifold, we'll care about this geodesic flow phi of t, which is the homogeneous version, and it is exactly the Hamiltonian flow of the psi variable, this psi, the length of the psi variable, and you can quantize this p here. It's exactly the square root of minus h squared Laplacian, and then you take the unitary group generated by this p, which is a half-wave operator, and this will be sort of a quantization of phi of t, which is reflected in the so-called Egorov theorem, which you have a symbol. You have a symbol a. You conjugate it by this u of t, this half-wave operator, and then you get a pulled back by this Hamiltonian flow phi t, or the geodesic flow phi t, and then quantize up to a lower order term. So, and the proof of this is exactly just by differentiating t, and you will find this. And you also have a very simple propagation, so-called propagation estimate, which you can control this side, this operator by oph a using this formula. So combining this result, you can easily, like in a half page, prove a version of our theorem like this. So as long as your function a geometrically controls M, meaning that every geodesic passes through A, passes through the open set A is greater than 0, then you get a uniform lower bound on A times U. So, and that is basically because you can use these two, combining these two to control all of the manifold M by saying the support of A composed with phi t in all of t, which covers the whole manifold M. So you can put this and this together to get this lower bound, and that is basically the simplest version of our result. But of course, it has a requirement that this A of the open set we have before must geometrically controls M. It cannot miss any geodesic.
This result is valid on any remaining manifold.
Yeah, this works on any remaining manifold. It works, and I think it's due to, well, it is not written explicitly in literature, but I think the geometric control condition is first in the work of Roch Taylor in the 70s. So.
And not necessarily compact.
It has to be compact. Has to be compact.
And the constant C appearing in the first estimate depends on.
Depending on A, of course, depending on M.
Depends on the size of the manifold.
Yeah. Okay, so you can see once you have this, the obstruction of our result is that you may have geodesics missing the open side we have, right? So that is the key to see. So all the other part we know how to do, essentially. Okay, so now let me come to the, before we go further to the proof, now let me come to the this semi-classical measure here. And as we say here, so we'll replace multiplication by a by a quantization of a, and this h is exactly the lambda 1/lambda, where lambda is the square root of the eigenvalue of u. So we take this limit, and the mu is the semi-classical measure. And by using very simple argument, you get first the support of mu must be in the cosphere bundle, and that is because comes from our normalization here, minus h squared minus 1. Okay. And okay, and it is also invariant under the geodesic flow. Okay. Which you can already see from here. Basically, if you can have something in A, you can flow it by the geodesic, and it must be kind of invariant. Okay. Okay. So there are many. Okay, there are. Okay, there are. So these two are the only thing you can deduce from the definition. Without any further assumptions. So there are many possible candidates. So the equity distribution corresponding to the Liouville measure, which is kind of the volume measure on the base manifold, and then the uniform distribution on the sphere, on the fiber. But you can also have the exact opposite, which is a delta measure along a closed orbit. That will be corresponding to the complete localization near this geodesic. And there are lots of possible candidates in between. This measure can have support in some fractal set that also happens. There are many things can happen. Okay, if you work on a sphere, then Laplace eigenfunctions are known, which are called spherical harmonics, which are just harmonic homogeneous polynomials in R3 restricted to the sphere. And you can compute, and there are actually a sequence of eigenfunctions concentrated on equator. And actually, these people, Jacobus and Zelditch and many people here, show that any invariant measure is a semi-classical measure. It can be obtained by a sequence of eigenfunctions. So in this case, there are nothing more, basically nothing more to say. So you can have all the possible things. On the torus, these things are very different. On the torus, Laplacian eigenfunctions are just sine, cosine, or maybe one is sine, the other is cosine. And there are also possible linear combinations of them, because the eigenvalues may have high multiplicity. It's just a sum of squares. And but this is already known. Of course, this is already known by Cook, Digman, and Bourgain, but they did not write in this language. But these are just questions about the trigonometrical series, right? So actually, any quantum limit, which means the limit we only consider on the torus, not lifting to the cosine bundle, is actually absolutely continuous with respect to the big measure. So you cannot have the worst scenario, which is a measure along a geodesic. So you cannot have this case. And for hyperbolic surface, okay, this can also be computed, at least numerically. These pictures are produced by Alex Stroheimer. And the key is that the geodesic law is called ergodic with respect to Liouville measure. I'll explain the definition in a moment. And there is a theorem called the quantum ergodic theorem, says that there exists a density 1 subsequence equidistributed, which means you pick almost all the eigenfunctions. So what's left is a so-called density 0, meaning in the first n eigenfunctions, you must choose small o of n. You must choose small o of n. which is density 0. And Rudnick and Sarnak has this quantum unique ergodicity conjecture saying that this is the only possible case. And which is of course that's not true. It's not true on the torus because you can easily fix L and taking K to infinity, you get something not the Liouville measure. So. And this conjecture is still far from resolved, so it's still very open. So okay. So the ergodicity condition means that any invariant, one definition at least, any invariant set energy flow has either Liouville measure 0 or Liouville measure 1. So either has 0 measure or full measure. And the quantum ergodicity just means that there is a density 1 subsequence which converts the Liouville measure. And the quantum, a very general quantum ergodicity theorem, which is first proved by Shnirelman in that's when in a conference like proceeding in Soviet Union, which is not known to the West or other. It is in the 70s and reproved by Colin Verdiere and Zelditch in the 80s, saying that the classical ergodicity implies quantum ergodicity, and these results are basically about the hyperbolic surface, and but then it's generalized to further systems like the so-called Bonimovich billiard, and you just consider this domain in R2, and the billiard flow is ergodic, and in this case you actually see that most of the eigenfunctions kind of equidistributed, but there are exceptional ones. And this one also called the hyperbolic billiard, which is analog of hyperbolic surface. So all the edges are concave, and this one actually that people believe to satisfy the quantum unique ergodicity, but it's not proved. Okay. Okay, the quantum unique ergodic just means so there is only one possible semiclassical measure, which is a Liouville measure, and actually this is the QE conjecture, and it is only known in the case of called arithmetic hyperbolic surface, which means hyperbolic surface which satisfies certain the quotient group satisfies certain arithmetic properties, and also in this case it also requires your eigenfunctions to be Hecke forms, which means it is also eigenfunctions of Hecke operators. Of course, it is conjecture that you have no multiplicity, so these are all the eigenfunctions, but it's not proved. So we only proved under the case of Hecke forms.
What did you say was conjecture?
It means that Hecke forms are joint eigenfunctions of Laplacian and Hecke operators. And it may turns out that some Laplacian eigenfunctions, some eigenvalues, Laplacian eigenvalues has high multiplicity, which you do linear combination, they are no longer Hecke forms. But it's a conjecture that this does not happen. Always multiplicity 1, but no one has proved or disproved of such thing. So okay, and there are also negative results. One negative result is this Bonimovich seeded. Or actually, in their construction, any manifold with or without boundary which has some kind of rectangular part or cylinder part. And in that case, Hassel in 2010 proved that, well, they actually proved almost surely, meaning almost surely the quotient of this length, the different lengths of this rectangle here, you have this concentration here. You have possible like exceptional sequence of eigenfunctions concentrated in this rectangle. And another model, which is kind of a discrete model, called the cat map, which you can also quantize in a way, which I'll explain, but it's also quantum chaotic things. And you can also define it. This will be like matrices, but the eigenfunction is eigenvectors, but you can have a representation in the on the torus, and in that case, actually, you have a non-QUE, which means you have this measure, which is a half delta measure and a half Liouville measure, is a semiclassical measure of some sequence. Okay. So what do we know for general compact hyperbolic surface now? So before our result, there is another characterization of semiclassical measure, which using so-called entropy, and they show that they actually prove an entropy lower bound for any negatively curved manifold. But in the case of hyperbolic surface, this lower bound can be computed, which is a half. And in general, this entropy is between 0 and 1, and equals 1 if and only if it's a Liouville measure. And when it's a delta measure, it's 0. So that means this result actually kind of exclude half of the possible candidate. So it's exclude all the things with entropy less than half. And our result is some kind of you can say some kind of transversal to this one, or orthogonal to this result. Meaning we have a result on the support, which means the support has to be the full cosphere bundle. And these two are does not include each other. So there are entropy bound. This entropy bound can exclude measures with some linear combination when this alpha is less than half. But we cannot rule out such thing because there is a part of Liouville measure here. And on the other hand, the entropy bound can only imply the dimension of the support is greater or equal to 2, Hausdorff dimension. And our result excludes a certain invariant measure with dimension very close to 3, so that the entropy is very close to 1. Okay. And I should also mention that neither of our result exclude things like this. This is kind of a critical case. And both of our method actually applies to this cat map. So unless you have some new input in our method, in either method, you cannot hope to beat that potential counterexample. Okay, so let me see how much time do I have. Okay, I have like 10 minutes. So let me try to use 10 minutes to explain the ingredient we are using in the proof. So what we actually prove is a so-called a control inequality, meaning that okay, so this inequality actually implies a lot of things, either the eigenfunction control or the semiclassical measure here. Basically says that you take any function which does not vanish on the cosphere bundle, you quantize it, and you look at basically this means you look at the part of the mass of U on the part of A, and this can control this together with minus h squared or partial minus 1 applies to U, together controls the whole function U. U does not need to be an eigenfunction. When U is an eigenfunction, this term is 0. So this expression here, log 1 over h over h, is actually short. So you cannot improve this one because of this example by Schwarz and Lindenstrauss and Schwarz and Silverman, and which they construct a so-called quasi-mode, meaning this one is a big O of this, and which kind of does not come to a Liouville measure, which has some scar here. So in that case, to violate this, if it violates this inequality, if we replace this by anything better. Okay, and to prove this is very similar to what I showed you before of this geometric control condition. Essentially, this part can give you everything by you flow out the you flow out the support of A by the geodesic flow. So well, you can do so-called micro localization things. Away from the energy surface, you can use this part of control, and on this part, you can use this one and the Egorov theorem to control everything which the geodesic flow kind of flows into this A here. And by this property change in an Egorov theorem. So the key enemy here is so-called trapped region, which means all the point whose flow line does not passing through this one. And the key upshot here is that that set is a fractal set, and it can be estimated by the so-called fractal uncertainty principle. And that is the idea of the proof. Okay. And okay. I will explain in a moment. So I'll actually show you in a moment. Okay. So let me quickly explain what does that mean by the geodesic flow is, and also it means along any flow line here, you look at the tangent bundle. It actually it's a three-dimensional thing. So it's M is two-dimensional. So cosphere bundle is three-dimensional. So the tangent space actually split into three subspaces. One is the flow direction E0, and there is a stable direction of contracting direction ES, which along the flow, the tangent vector is getting shrinking exponentially, and there is also an unstable direction which it gets expanded exponentially, and it is actually so that means if you have a small ball here, after a very long time, it will kind of get stretched very thin and very long. And on this hyperbolic surface, you can actually identify these spaces by using Lie group theory, and you actually find that these are actually invariant vector fields. Okay, and okay, so when we prove things, we first discrete the time, and we first pick a partition of unity. One is A1. A1 is supposed to represent the control part, and A2 is the part which you cannot control, basically. So A1 is the one can get a control. A2 is cannot control, and we require both parts actually miss something. And then you do the Egorov theorem, you can see that each part under the by conjugation of the Liouville operator gets stretched. You can actually pull back by phi t, which means this A1 will be stretched thinner and longer. And okay, this is some technical, but this is well-known techniques to use like word of 1, 2 to do a refinement of partition, which means at each step you do this partition, but by conjugate by this time t here, and okay, somehow here it okay. Sorry, I think I need a different page. It works here, but it does not work here actually. So, so in any case, okay, let me just try to say briefly what's going on. But basically, we try to this n1 is like log h, so log 1 over h. So and then you each of these will represent a pseudo here. Each one of this will represent a pseudo differential operator, which means you like have A1 and some A1, some A2 stretched by 1, some A1 or A2 stretched by 2, and so on, and multiply them together. and you get this thing here. And then you get a partition of unity by AW. W is a word of length log 1 over h, which each upper beta is 1 or 2. And the key is that this AW is actually, the norm is bounded by a small power of h. And why is that? Because each AW here is a product of something A minus or something A plus. And each A minus, A plus, the spot of A minus and A plus is actually a very fractal set. So which I'll show you why in a moment by a picture. Okay, I cannot draw a three-dimensional picture, so I use this cat map as a model, which works exactly the same. So a cat map is just you stretch in one direction and shrink in another direction, and the matrix is 2, 1, 1, 1 on the torus. And okay, and I want to remove a disk, the image of disk at each step. So if I remove one here, it will turn out this. I remove another iteration here, and you'll just keep removing things further and further. You'll just see. Okay, what's left is just a moment. Okay, something like this, which is a very fractal in this direction and very smooth in this direction. And if you do backwardly, you just keep change the two directions. So, well, on the manifold, heuristically, using so-called free integral operators, you can change this stable and unstable direction into something like the position and the frequency. So that turns out to be the so-called the fractal insertion principle, meaning if you have two sets which are both so-called porous, which means you have lots of holes in this set, and if you use this Fourier transform, put into the middle and you cut off in both sides, and then the norm of this one, which works exactly like the operator I have before, heuristically, it has this bound L2 norm bound, like h to the positive power here. And this is the fractal insertion principle proved by Bourgain-Dyatlov in 2018, and the one we are using here. So why it's called a fractal insertion principle? Because it means that a function and its Fourier transform cannot be both localized near fractal set, which is the Euro insertion principle means you cannot localize near a point. So it's a generalization of the, for example, the Heisenberg fractal insertion principle. And it's actually first proposed by Dyatlov and Zhao in 2016 to study another type of quantum calculus system called the open quantum calculus system, and it's proven in one dimension by Bourgain-Dyatlov, which is the one we are using, and a discrete version is given by myself and Dyatlov, and there are quantitative version which gives you the relation of beta and x and y with the joint work with Dyatlov and Zhang Ruixiang. And there are some higher dimension results by Hanschlag, Plagative Tau, and Beckerslang Tau. It's different Tau. This is Terence Tau. This is Tau Zhongkai. And Cohen. With this one actually is the most general one we have so far. But we haven't have any application yet. So, okay, and then you can basically the thing works as follows. So basically, you separate the you do partition unity by a controlled part and trapped part. I think my time is up. And for simplicity, you can do a rough version, which means the controlled the controlled part is one. If you have any alpha beta 1, you get a control. Okay, and this part we call y, and the trapped, which is the missed part, which is x, consists of one word. And if you do this, you can put y, like do a decomposition of y by the first one, which is control. The first time is control. And then very easily by by a estimate. You separate this AY by all this AYL, and each AYL can be estimated by the propagation estimated by controlled by A of U with something here, and then you sum them up, or you get a slightly worse thing. You have log 1 over h here, log 1 over h squared here. Okay, and this AXU part is given by this fractal uncertainty principle, which is a small power of h, and you put them together, you can absorbing this small power of h in this side. You get this estimate. Of this estimate is very bad because it's log 1 over h, which goes to 0, it goes to infinity when h goes to 0. And okay, then we use the idea from Shnirelman's paper in 2008, which means you do a better thing. You want to say that the controlled part you have to control at least a small portion, which appears in this appears in A1, and the rest is x. And then you do a combinatoric counting, which means x has at most the h to the minus c square root alpha that many elements. So if we choose alpha very small, so c square root of alpha is less than beta, then each of things in AX can be controlled by this. So the total thing can be controlled by this times this, which is still a positive power. So that will work in X. And for this one, you can break into a fixed number. In our paper, we break into 8 one instead of the previous case. In this case we did like log 1 over h many of them. So, and that basically finished the proof. So, remove this log 1 over h here. Okay, so and we have like, I think my time is up, so I'll just quickly mention the results also have applications in so-called control theory of linear Schrodinger equation and damp wave equation. And there are many further questions to be asked, and there are some results we already know by, for example, the CatMap, and there are also here. So here is mistype. So we also generalize this to the two-dimensional and also manifold, as mentioned before. And the recent result of Dyatlov Miller has certain generalization, not every complex hyperbolic quotient, which is a higher dimensional hyperbolic manifold, but some of them. And there are also the question about whether we can prove similar things on Euclidean domains with concave boundary, which is still not known. And eventually, you want to not only know chaotic system, but you also want to know a mixed system, which have some part integrable, some part chaotic, which let me just stop here by showing an example, showing a picture here, which is a hydrogen atom in strong maximum field, which has this island of integrable part and kind of a sea of chaotic part. So, and so I'll stop here. Thank you.
Thanks for the talk. Any question?
My question is, do you prove quantum unique ergodicity?
No, we do not. We do not.
You do not.
We do not. We prove kind of.
But the measure that you get, the
measure we get, we can say it has full support, but it may not be
invariant.
It is invariant, but
then you're done.
But it may not be the Liouville measure. It can be a Liouville measure.
No, but you know it's absolutely continuous.
No, we do not know it's continuous.
I thought that was.
That's only known for the torus. We do not know for the hyperbolic surface.
So the challenge is to prove that it's absolutely continuous.
Well, I don't. The way to prove it's absolutely continuous is to use for the torus is to know exactly the Fourier series properties. So so it does not really work in this case. So you can of course try to do that, but I don't think. I don't think it has. It's easier to do. So, okay, so for example, even if you want to prove it cannot be a delta measure, well, there is no simple proof of that. You either use the entropy bound or use our result. So there is a what? Okay. So it's not that easy.
Any more questions?
So to what extent can your result be extended to non-compact domains?
Non-compact? Well, okay. On non-compact, then you want to ask what are the replacement of eigenfunctions, because on non-compact manifold it usually has a continuous spectrum. Okay, so you can, well, in hyperbolic surface, hyperbolic case, you can use called the Eisenstein series, which I don't think is known, except in the case of this. Except in the, I don't think it's proved so in the hyperbolic case. Or you can use called resonant states, which are okay, which is actually conjectured only supported on some fractal set. So actually, which there are some results, but it's not clear what is the goal here, because you want to ask what is the replacement of it. Yeah, for modular surface, if you use the hack form, then it's known. That's the arithmetic one. Okay. And it's not known in any other non-compact case. Okay, quantum ergodicity is known for Eisenstein series, but quantum unique ergodicity is not.
Thanks.
Thank you for the talk. Can we extend this result to the general Schrödinger operator, like the Laplacian plus the magnetic field or the potential term?
Yeah, at least for the potential, there is no problem, because okay, the key estimate here just turns to that page. Okay, if you just put a plus b here, then you have h square, which is square beats this one. So you can always absorb that part into this set. So plus b is always work. So if you if you add a magnetic field, that may change I think that may change. Okay, depending on how do you add magnetic field. So which power of h you put it for that. You put h squared. Okay, it's a first order operator, so it's not clear whether you can extend that case. But at least for Schrödinger operator, you can certainly.
Oh, thank you.
Any more? Okay, I think Professor Jin again.